We're here where we left off in part one at compound reverted gear trains, and we're going to continue on for part two of chapters 13, 14, and 15. I'm going to try to make this as painless as possible by skipping, as I mentioned in part one, skipping a lot of information, packing just the topical content of importance of chapters 13 through 15 into these slides. So we left off here pretty much at planetary gear trains. Sorry, I have to put my phone on mute. That wasn't your phone, it was mine. They're just typically called planetary. Let me get back to the insert menu. Sorry, draw menu. Planetary. The book says or epicyclic, but I've never actually heard that term before outside of this book. Always just heard of it as planetary gear trains. These are common in automobile automatic transmissions. At least they used to be. I guess they're going to CVTs now. But you have a sun, a planet, and a planet carrier or arm. Those are the three main parts: the sun, the planet, and ring gear, and the arm. And this has 2 degrees of freedom. So you can have two different inputs. That's really unique about this. You can get a lot of different transmission ratios out of this. That's why they're a popular compact um, uh, component of an automatic transmission. If you're not familiar with these, um, in various configurations, all of these gears can rotate, including the ring gear, but they don't all necessarily need to rotate. So you could have one of them fixed, or none of them fixed, or you can change gear ratios by locking one up. For instance, if you prevent the planet from spinning around its own pinion, then that definitely will. Or if you lock up the arm, that definitely causes a different type of motion than if the arm is free to swing. Here, the train value is defined differently than the previous gear trains. In this case, we're just looking at the first, last, and arm. So it depends which is the ring or the sun or the planet, the output gear. So you don't know. You need to know which is the input gear and which is the output gear. So you have three gears to choose from. So NL. Sorry, those are lowercase. These are speeds. So N is a speed in RPM, and L is the last, F is the first. So last would be the output gear, first would be the input, and you have three to pick from. You have the, and A is the arm. So you have three to pick from here. You could have the ring, the planet, or the sun. Could be any one of these two. So you have the ring, planet, and sun could all be L or F, obviously not at the same time. So that's why this is really configurable. You have three gears, and any one of them can be the first one, and then you eliminate that from the list, and either of the remaining two can be the output. So now we're again, the book does this. It kind of hops around. I would have put this back with spur gears for consistency, but they have a whole force analysis section for all the gears. So this is where it ends up in their chapters. Um, it's important that you recognize the this is the forces and gears specifically for things like calculating output torques and diagnosing problems. So if you're having some sort of failure and you have some sort of wear or wear pattern, it's important that you track that back to what you know should be the actual forces. And if you're getting a wear pattern that doesn't coincide with the expected forces, then you have to start looking for what unexpected forces could be causing that wear early failure location. Here we have the load on the at the pitch circle is not entirely tangential, but keep in mind that only the tangential component is going to give you any torque. The rest is just loading up the bearings. So here they have that um, um, laid out. This would be the load that's transmitted load for torque. They're calling it W sub T is F sub 32 tangential. And so only the tangential component of the force of 3 on 2 gives you any uh, uh, useful load for torque. And then we have, of course, the equation for torque based on that. Power, transmitted power is based to the based on the tangential load. So this is fairly important. What kind of power can you expect to be transmitted through? And of course, it's related to the rotational speed. And typically, omegas are in radians per second. So omegas are generally in radians. That's speed in radians per second. That's the convention. I need to take a minute here. The kid just unplugged his headset. Give me just a second here. Yep, I had the kid watching a movie and he unplugged his headset. So let me get him plugged back in. And then we'll get back to the lecture. Sorry about that. See, little buddy, when you move away from the movie, the headset unplugs. He was being so quiet, too. Okay, so I got the kid back watching his movie, Cars 2. And he did it again. So give me just a second here. I'm going to just stop the movie. You're going to hear a kid in the background now for the balance of the lecture, but I'm deep enough into this, so I'm going to let him just make noise in the background. Okay, the only thing I haven't described here is pitch line velocity. You have this 12 here because they're defining pitch line velocity in feet per minute. That's why there's that random 12 hanging out there. Power. So here's some useful power relations in customary units. So we have pounds force, horsepower, and pitch line velocity in feet per minute. This is all common customary units. And then they have the SI version too. This is the SI. So this is I used to teach this class and say I didn't teach anything in SI units because I said the vast majority of you are going to be working at an American-based company, and they all use English units. I've found that lately to be not true. That there's been a radical shift lately. I've noticed a lot of domestic companies are actually shifting to SI units, mostly for their overseas customers and their overseas supply chain. So it's just a lot cheaper to get metric nuts and bolts and design everything metric and sell it to people who use metric and replace parts with metric. So eventually we're all converting at this point, I believe, to eventually to metric. Anyhow, when you get to bevel gears, the force analysis gets a little bit dicier. If you have a gear like this and it's failing, just reference back to this picture and see, okay, compare your failure or your wear to these known set of forces, right? And for helical gears, you can see this is getting pretty complicated. Um, I'm not particularly going to hold you responsible for the bevel gear and helical gear equations here, like WR, WT, and WA. This is just to give you some idea of how complicated the loading is on these teeth. Practically speaking, for any kind of force analysis you need to do on these, I would again use FEA. Use FEA if you need to do something like this. But FEA is not going to pick up the manufacturing variations and all that sort of stuff. Um, you know, the so sometimes a direct inspection is what's best. So here's where we do a whole bunch of skipping, chapters 14 and 15. Sections 14.1 and 14.2 are historical, elementary, and not in general use. So we don't even need to worry about that. Sections 14.3 through chapter 15 follow the AGMA approach to gear stress calculation and design. And although that is a very useful and very well used method for designing gears, the chances of you ever using it are minimal. Furthermore, the course text really only gives the course text really only has a partial presentation. That's the most important part. They do like one example of one type of thing, which is really not representative of the scope of the full AGMA procedures. This is something you need training on in order to effectively do. So really, in this book, this is meant as just an introduction to the AGMA approach. And from that, one thing you should be able to tell right off the bat is that this is a very intricate and detailed set of procedures. In other words, they have you doing one example, one tiny little example, and it's taken up, like an entire chapter. Um, so this is material to go in detail for a course that is specifically on gears or a technical elective or a training session, like a 20-hour training session or 40-hour training session on gears. Really, this is an example in the book where it's a very complicated and extraordinarily introductory uh, treatment of the material, if that makes any sense. In other words, let me repeat that. It's very complicated and detailed and intricate and very introductory and basic. That should give you an idea of how difficult and involved the AGMA approach is. And so it's really just kind of showing you, hey, this is how hard it is for the simplest example we can give you. So this section of the book is not meant to make you, at best, like an expert at AGMA approach. Okay. Uh, what this boils down to is you're only responsible for the material in chapter 14 and 15 that is in these lecture slides. And otherwise, you're not responsible for examples 14 and 15. So you're not responsible, mercifully not responsible, by the way, because when I show it to you on the next slide, it's pretty dicey. If you want a summary of the AGMA procedure for spur gears, you can either look at the, and this is just for spur gears on the next slide. It's either, you could look at the next two slides, or there's a bunch of links out there too. If you find yourself at a company that does do gears and you need to self-educate, there are a lot of, I just found these links. I hope this one's still active. It's from 2013. Just Google spur gear design, and there's a bunch of OEMs that have free learning materials out there to help you out. It's pretty cool. Anyhow, this is a summary for bending of gear teeth. This is part of the AGMA procedure here. It seems to look pretty ugly. It is. So this is AGMA. for spur gear. Um, you've got all of these coefficients that need to be found from a table somewhere or an equation. So they do actually point it out to you, but you see that they're cross-referencing just in this for the stress equation here. I mean, they're cross-referencing, stuff from, a table below, multiple equations. It's just very complicated, um, very involved. Um, and you have to make sure that all your units match, or you could really screw things up. And I would say that the chances of you needing to actually apply the AGMA methodology to design your own spur gear is so remote, which is why we're not really going into this in any kind of depth. This is just to show you that if you want to do something like that, this is partially what's involved. This is the next page of this. This is the summary. So it gets even uglier. So it gets uglier, and it's not even done yet. Um, so I mean, this looks ridiculous. You've got this formula with like 10 coefficients, and you got to go through and read the section that each one of these equations is in, make sure you understand everything, have it in the right units, then apply it, and then combine it with the previous sections to make design choices. That's why you're really not going to do this yourself. I wouldn't do this myself unless I seriously had a reason to. If I needed to design a gear, a custom gear, you want to guess how I would do it. And since you're not actually sitting here, I can't actually have you guess. I would actually hire somebody who's a specialist with gears to go ahead and do that. I mean, I've got a PhD. I've been teaching this material. I've been through the AGMA procedure. I went through this, teaching this class a number of times. And I just dropped it because I realized if I ever actually had to do this for my own application, I would hire somebody who does this for a living or has done this for a living for a number of years, because there's just so much involved. If you're gonna apply this, you need your own custom software that already makes sure that all the units aren't screwed up. This is definitely something you don't want to do by hand the first time through and count on it working. This is something you need to like program in your own custom MATLAB or Excel spreadsheet or something to bookkeep and keep track of everything so that you know that you're not making stupid computational errors. It's pretty complicated. Uh, so instead of going through the AGMA um, problem in detail and flogging you with that, I'd rather focus on some practical information for the balance of the lecture that is not in the textbook. You are still responsible for this. So, some practical information on selecting gears. Um, basically, before you contact an OEM, know what your power, torque, speed, and size, and form you need. That really helps. And then really go directly to a power transmission OEM and buy the appropriate off-the-shelf components. That's my first two main uh, pieces of advice. And then I've gone through. Here's a partial listing of some power transmission companies. I don't know where I found this link, but I found it while researching for this lecture. Um, if you want to get more into detail with it than that, then you really need to take AGMA training. The AGMA education site is here. And you should just go to that site and check out all the courses they have. It'll give you some idea of how complicated gear design and failure analysis is. There's also these practical websites here, Gear Technology and the basics of gears. Also some modeling of involute gears and SolidWorks, some tutorials. It needs its own tutorial. That's how difficult it is. I actually, to be honest with you, I didn't watch that tutorial when I designed my own involute in SolidWorks. I forget what these videos have. I knew what I was doing, so I just did my own thing without watching a tutorial. But if you're going to attempt something like that, you would definitely want to watch a tutorial before going into that. Some more practical information, gear fault analysis. This is also not in the book. When gears fail, sorry for the small print, we can zoom in on this a little bit. So, you're generally going to have heat, vibration, noise, and if you can see it, wear. You might get chips in the oil. Inspect your oil. Always inspect the oil. There's a number of reasons why you could get faults. Poorly cut gear profile, gear misalignment, lubrication issues. This could be contamination issues too. Could have some other procedure that's dumping metal chips into your gear lube. You could have misalignment, unexpected dynamic forces or torques, unexpected reversals of torque. You could have a bearing failure. There's all sorts of stuff. These are nicely summarized in the next slide. Another external thing that I found that's not in the book. If you're going to do a direct inspection and make a damage report, look for surface wear and bending failure at the root. That's the main thing. That'll tell you most of what you need to know if the gears failed. Get that information, take pictures, send it off to the OEM, and call in the A-team. And then also determine if the wear is evenly or unevenly distributed. If it's unevenly distributed, that means you probably have some sort of misalignment issue or improperly cut gear profile. So, the distribution, basically the location and distribution of the wear both indicate the root cause. You can also, do a vibration analysis, measure the vibration and look for gear mesh frequencies. My voice is getting a little, I'm trying to drink water here, but my throat is really dry. Sorry. You could probably hear it drying out. I'm going to take a sip of water here. If we're going to do what we did in measurements class, a dynamic analysis with the fast Fourier transform, and I've got an actual slide of this actual consulting project I did for gear fault analysis, where I apply this dynamic analysis and look at the gear mesh frequencies. That's what you're looking for. The gear mesh frequencies and their sidebands will let you know which specific gear is the problem. So this was on a compound gear set, and through vibration measurements and FFT, I was able to identify the exact gear in the train that was causing the problem. Turns out it was the input gear, and it was improperly cut. And I knew it was improperly cut because I asked them to do a contact check, which is the last thing here on the gear fault analysis, where you put layout blue on the gears. You drain out all the oil, clean it all up, put layout blue on the mating gear sets, and turn it by hand, and do a contact check. If you, this is also useful. Gear mesh frequency calculator. I wish I had that for that consulting project and my all sorts of other projects that I did where I didn't have that. I had to always calculate that by hand. I always went and got the same book out of the same library at Case Western, and eventually made a Xerox copy of that, but I don't need it anymore because now we have online tools that'll calculate gear mesh frequencies for you. Gearbox failures, again, all this isn't in the book now at this point. This gives you an idea of all the things that can go wrong with your gearbox. From resonance to bearing failures, thermal instability, other types of bearing failures, gear misalignment, manufacturing errors, external contamination, unusual starting torques, lubrication debris, and unexpected loads. I kind of covered a lot of that in the previous ones. And again, this is a really good graphic. So I've never really heard of Neil Consulting Engineers outside of this. They just came up on a highly ranked, link on a Google search of gearbox failures. But the fact that they put together such a nice, concise graphic and made it publicly available, I would say that they probably know what the heck they're doing. Unfortunately, they appear to be in the UK, but that doesn't mean that they wouldn't be happy to work on your gear problem for you, or your gear solution rather. I don't have anything to do with them, but I included them. All my sources here I referenced, but this is just an example of just how much information there is available out there. This is an actual case study from my uh, field troubleshooting of a large gearbox. And the following pages, this is the last part of the lecture, have an excerpt from one of my numerous consulting projects on a large industrial gearbox at a steel plant. This is a plant where they're taking sheet steel and making it into uh, basically less wide sheet steel to eventually be stamped into what do you call it, washers. So they're starting with like a 6 foot wide, the pieces, the sheets, the rolls of steel you see going down the highway. They take one of those and they cut it into like 1 inch wide, half-inch wide strips, bundle it up and send it out to be stamped into washers. Uh, the gearbox manufacturer actually retained me, not the steel plant. The steel plant was experiencing, sorry, I need some water here. They were experiencing a lot of gearbox failures, not just at this plant, but at a bunch of places where this gearbox was deployed, this classic gearbox. And this just happened to be the closest um, gearbox to me physically, like geographically. So that's where the gearbox manufacturer sent me. So they wanted to find out what's going wrong with their gearbox. This is a compound gearbox with about a 600-to-1 gear ratio, which is pretty heavy duty. And the problem was so bad that the shaft seals were melting. There are high levels of noise and the noise and so high temperatures, high noise. But of course, temperature and acoustic measurements didn't do anything useful. So that didn't do anything. However, a dynamic analysis of the vibration did identify the offending gear mesh. The gear mesh frequency, the most obnoxious one, matched the first pinion and gear set, and the side banding matched the gear rotational speed, not the pinion. So that pretty much identified the first gear in the train was the one that was screaming. That's all from vibration analysis. Based on the vibration analysis, I had them blue the shaft, put layout blue, and it turned out that it did not have proper contact. And the gear supplier, let me pick a different color here. The gear supplier, the gear supplier to the gearbox manufacturer had sworn up and down that there is nothing wrong with their gears, and it had to have been misalignment of their gearbox or their tolerancing. He pulled up every other thing that they could have screwed up on that gearbox and blamed it on that instead of the gears that he supplied. And after they blued and turned that set of gears and showed him the results, he couldn't argue anymore, and that gear supplier was forced to recut and resupply all of the problem gears in this classic gearbox. And he looked like a total dirtbag in the process because my customer was trying to tell him it was his gear all along because they'd pulled one of these gearboxes apart, and they just wanted a more professional PhD level opinion, which they got impartially from me. I didn't even know that they had this gear supplied by somebody else. I went through and identified in an honest and professional fashion with a dynamic vibration analysis where I thought the problem was, recommended layout blue and hand turning, the gear set to see a contact check. And by the way, I didn't just do all this in a vacuum. I called my contact at John Deere before proceeding with this project. I educated myself with a guy who has got a PhD. His subject was specifically in transmissions and gears. He's in charge of a research lab for transmissions, which is all gears, at John Deere. He lives, eats, and breathes it. He owns his own farm. He runs his own tractors. He does this like every minute he's awake. He's not with his family. And so I called that guy. He's a friend of mine. We went to school together for our PhDs, and I educated myself, so I knew going in a little bit better what to expect. But um, essentially, I successfully found the problem. Here's parts of the excerpts of the report. This is what the vibration measurements look. You can read all this and all that sort of stuff, but this is what gear mesh frequencies look like. So this is your gear mesh frequency. This is what I wrote and what I put in a report. And you see it's not real clean because it has these side bands. So the gear mesh frequency is how often two gear teeth slap against each other. That's all it is. So this gear mesh frequency corresponds to how often two teeth slap up against each other. These little side bands will tell you which one of the gear set it is that's causing this vibration, either the pinion or the gear. Here's a close-up. So this is a close-up. This is the main mesh frequency. And you can see the little side bands. And it's the spacing of those side bands that determine which gear in the gear of the pinion in the set is actually causing the problem, causing the interference, causing the undercutting, causing the gear failure, causing the obnoxious heat, vibration, and noise problem. That was a successful troubleshooting mission, to say the least. I'd like to conclude on something even more awesome than that. And this is automobile gearboxes. Again, I could teach a whole course on this, but I could take easily 3 hours to talk about it, but I'm not going to do that to you. I just want to guide you to some of the more cool links that I found while researching for this lecture on applications of gears. And this is really just go find it on your own. But these, if you copy and paste these links into YouTube, you'll see some pretty interesting animated videos of what's going on in your car with manual transmission and the synchro mesh. If you've never heard of synchro mesh before, then you need to know what a synchro mesh is. It's pretty cool stuff. Life before the synchro mesh was pretty rough. You had to speed match your gear sets, lots of grinding, lots of metal shavings being created. Then we have the automatic transmission, and if you've never seen an animation of an automatic, a traditional automatic planetary gear set transmission, you haven't lived as a mechanical engineering technologist yet. I implore you to watch some of these videos. It's really neat. That's the last slide I got. I'm not going to take any more of your time here. Just get back to slide number 1. And actually, this is my favorite slide. Let's end on this one, the dust mite working on his transmission. Sometimes I feel like that too. Just an insignificant speck of nothing, working on a problem there that's way beyond me. And, basically you just got to educate yourself and try to just put yourself in deep water and know that you can swim. And that'll do it. Let me reattach my keyboard so I can hit the stop recording button. And we got one lecture left after this, and that's it. So hopefully this is going okay. I'll find out when the student reviews come in if this is working or not. And that's all I got for you. See you for the last lecture.